Mars Climate Orbiter's Lost Units A unit conversion mistake destroyed a $327 million spacecraft before it ever reached orbit. NASA launched the Mars Climate Orbiter in 1998 to study the planet's atmosphere and relay communications for future missions. Lockheed Martin built the spacecraft and wrote the navigation software, while NASA's Jet Propulsion Laboratory ran the mission from the ground. And the two teams needed to exchange thrust data using the same measurement system. Lockheed Martin software calculated thruster performance in pound-seconds, an imperial unit of force, while JPL software assumed the values were already in newton-seconds, the metric equivalent. The mismatch went uncaught. As the orbiter approached Mars in September 1999, the faulty data caused it to miscalculate its position, and it drifted far closer to the planet than planned, either burning up in the atmosphere or continuing past it into deep space. NASA had spent nearly a decade planning missions that depended on this orbiter's data. Afterward, NASA introduced mandatory unit verification checks across every mission, a rule that traces back to two teams who never confirmed they were using the same units. The Gimli Glider's fuel conversion A rounding error and a fuel calculation forced an airliner to become a 150-ton glider. Air Canada was switching its fleet from imperial to metric measurements in 1983, and Flight 143, a Boeing 767, was among the first aircraft affected. Ground crews needed to calculate the fuel load, and since the plane's gauge was malfunctioning, the amount had to be measured manually and converted by hand. The crew applied a conversion factor meant for pounds, as though the result were already in kilograms, understating the fuel needed by nearly half. The aircraft took off believing it had enough fuel to reach Edmonton, when it actually had less than half that amount. At 41,000 feet over Manitoba, both engines flamed out from fuel starvation, leaving the plane without power. Captain Robert Pearson, who had glider training, and First Officer Maurice Quintal guided the powerless aircraft to a decommissioned airstrip in Gimli, Manitoba, landing it safely with no fatalities. The incident became a textbook case in how conversion errors slip through when a system changes standards mid-operation, and it's still known as the Gimli Glider. Ariane 5's Integer Overflow A, number 2 large for its own memory space, destroyed a rocket 40 seconds after launch. The European Space Agency launched Ariane 5, a heavy-lift rocket that cost roughly $7 billion to develop, on its first flight in June 1996. The guidance software was largely reused from the earlier Ariane 4, which flew at a slower horizontal velocity, and it converted a 64-bit velocity value into a smaller 16-bit format, a process that had worked on the older rocket because its velocity never grew large enough to cause a problem. Ariane 5 accelerated much faster, and the value exceeded what the 16-bit format could hold, triggering an overflow error the system couldn't handle. The guidance computer crashed, the identical backup computer crashed moments later, and the onboard software misread the failure as an extreme flight deviation and tried to correct it, tearing the rocket apart. The explosion destroyed 4 scientific satellites along with the rocket, a loss estimated at $500 million. Investigators found the failure came entirely from software written for a rocket that no longer existed. Sleipner A's miscalculated shear stress and underestimated stress calculation sank a concrete oil platform the size of a skyscraper. Sleipner A, built for oil production in the North Sea, was undergoing final ballast testing in August 1991 before being towed to its drilling site. Engineers had used a finite element analysis program to model how the concrete cell walls would handle water pressure at depth, but the software's mesh design underestimated the shear stress in a critical wall section by roughly 45%. Leaving the concrete reinforced for far less pressure than it would actually face. As the structure was ballasted down near Stavanger, Norway, one of the cell walls failed exactly where the calculation had understated the load, and water flooded in faster than pumps could clear it. The platform sank within hours, registering as a small earthquake on nearby seismographs. No one was killed, but the loss, including the platform and cleanup, ran close to $700 million. Investigators traced the failure to the software's mesh model, not the concrete or construction. The Tacoma Narrows Bridge's Resonance A miscalculated response to wind brought down a brand new suspension bridge in under an hour. The Tacoma Narrows Bridge opened in Washington State in 1940, one of the longest suspension bridges in the world, built with a narrow, shallow girder design meant to look sleek and save on materials. Engineers had calculated wind resistance mainly as a static force, treating it as a steady push rather than something that could interact with the bridge's own motion. And the design didn't account for aerodynamic flutter, a self-reinforcing twisting motion that can build when wind flows across a flexible structure at the right speed. On the morning of November 7, 1940, moderate winds of around 40 miles per hour caused the deck to twist and oscillate with increasing violence, a motion later captured on film. Within hours, the twisting grew severe enough that the deck tore apart and collapsed into the water. Only a dog left inside a car on the bridge was killed. The collapse changed how engineers calculate wind loads on suspension bridges, making aerodynamic testing standard for large-scale bridges that followed. The Vasa's asymmetric hull A ship, built with mismatched dimensions, capsized and sank less than a mile into its first voyage. The Swedish warship Vasa launched in Stockholm in 1628, one of the most heavily armed vessels of its time, commissioned by King Gustavus Adolphus during a war with Poland. Shipbuilders of the era worked without formalized stability calculations, relying on proportional rules of thumb passed down through experience. An archaeological analysis of the wreck later showed the ship's port and starboard sides had been built to different measurements, likely because two teams of shipwrights worked from different standards, throwing off the center of gravity. A second heavy gun deck added late in construction, without adjusting for the added top-heavy weight, left the ship with far too little ballast relative to its height and armament. The Patriot missile's clock drift A, tiny rounding error in a computer's internal clock, let a missile through and killed 28 soldiers. During the 1991 Gulf War, Patriot missile batteries intercepted incoming Iraqi Scuds by tracking their position with an internal clock that measured time in tenths of a second and stored it as a 24-bit binary number, which couldn't represent 1/10 exactly, much like 1/3 can't be written exactly in decimal. Each measurement carried a small rounding error, and normally the system was rebooted often enough that it never grew large enough to matter. On February 25, 1991, a battery near Dhahran, Saudi Arabia, had been running continuously for over 100 hours, letting the error accumulate to roughly a third of a second, enough to throw off a Scud's calculated position by more than half a kilometer. The software determined the target was outside its tracking gate and dropped it, so no interceptor launched. The Scud struck a U.S. Army barracks, killing 28 soldiers and injuring around 100 more. A patch that would have corrected the drift had already been written and was en route. It arrived one day after the attack. Long-term capital management's impossible correlations A set of financial models built by Nobel Prize winners nearly broke the global banking system. Long-term capital management was a hedge fund founded in 1994 whose principles included two economists who later won the Nobel Prize for their work on derivatives, and its strategy relied on models that calculated risk from historical relationships between markets, assuming certain assets would never move in the same direction at once. When Russia defaulted on its debt in 1998, global markets moved in ways the models had treated as virtually impossible, with assets across unrelated markets suddenly moving together instead of offsetting each other. The Reinhardt-Rogoff spreadsheet error, a missing row in a spreadsheet, helped shape years of global economic policy. In 2010, Harvard economists Carmen Reinhart and Kenneth Rogoff published research arguing that once government debt crossed roughly 90% of economic output, growth slowed sharply, a conclusion widely cited to justify austerity after the 2008 financial crisis. In 2013, a graduate student and two professors at UMass Amherst obtained the original spreadsheet and found a coding error. An Excel formula had accidentally excluded 5 countries from a key calculation by failing to include all the relevant rows in its average. Correcting it, along with other methodological choices and how the data was weighted, substantially weakened the growth cliff the paper had described. By the time the mistake surfaced, the 90% threshold had already been cited by legislators and finance officials to support budget-cutting policies affecting millions.